So today I'll be talking about the research work that we have done in order to explore energy efficiency in traditional AI or neural systems with this spike-based machine intelligence or what we call as neuromorphic computing. Now, before I go forward, I just want to thank all my students and the sponsors who have supported this work. Now, the motivation for energy efficient AI, if you think about it, it comes from both a demand and a supply perspective. So, from a demand perspective, we know that today we live in a world where we want to embed intelligence in every technology that surrounds us, including some of these very low power devices, as shown here, your smartwatches, your mobile phones, that work with a few watts or milliwatts of power, right? And putting these compute intensive AI algorithms on them can really be non-trivial in terms of how do you come up with a more efficient and resource constrained manner of implementing these algorithms. Then similarly, if you think from a supply perspective, what we have seen is that in the pre-GPU computing era, the trend in terms of the computing performance of these AI models were almost at par with what was Moore's law or advancements in hardware. Whereas in the post-GPU computing era, with the advent of GPUs, the sort of deep learning revolution began, and the type of computing performance that today's networks demand, which are like GPT-3s or BERTs, etc. Now, those kind of compute performance demand is doubling almost at the order of 2 months or 3 months. So as you can see that the compute demands from deep learning workloads is increasing at a much higher rate than that of the current advancements in hardware. So there is a need to think about hardware efficient AI algorithms. And this is where spiking neural networks or spike-based machine intelligence can come into play. Now, with the whole motive of spike-based machine intelligence is to take inspiration from the brain. And if you look at the brain, our brain, we perform impressive feats, not only just recognition, but also a whole lot of other things in terms of reasoning, the fact that I'm moving my hand, I'm talking, all of that is happening with a meager power budget of just 20 watts. And whatever little is known of the brain, there are two things that are potentially the reason why this power budget of why the power budget of the brain is so low. One of them is spike-driven computation and communication. That means neurons in the brain communicate with sparse temporal spikes or binary events. So that leads to a lot of efficiency. And the other thing that also helps in this reducing the power budget is the fact that brain is a 3D structure wherein these neurons and synapses are intertwined or kind of collocated. So that can again lead to massively parallel, high throughput, and extremely efficient computations. So in the field of neuromorphic computing, we are trying to use spiking neural networks as a means to integrate some of these spike-driven computations and communication-related cues from the brain to harness energy efficiency, as well as to see if this temporal way of processing things using binary spikes can also lead to improved learning capability. And on the hardware end, we are trying to use these non-volatile memory-based in-memory computing architectures, which is this analog way of computing things in order to do very efficient and high throughput computations. So in terms of like why I do in our lab, some of the motivation behind SNN research is essentially to think about, as shown here, like we want to really figure out or investigate if SNNs can have a better scaling trend in terms of computing performance than what today's traditional neural networks give us. And to answer this question, we are trying to figure it out in two ways. One is, can SNNs combined with appropriate in-memory computing architectures fill this performance gap while maintaining energy efficiency? And on the other end, there is a need to also think about which type of an application can maximize the potential of SNNs such that you can have a better scaling trend. So to that effect, in order to answer these two questions, in my research group, we have been looking at it in a both algorithm as well as a hardware point of view. So from the algorithm point of view, we are focusing on a couple of research thrusts. The first research thrust is really thinking about algorithm development for building high performance spiking neural networks, which involves how do you accelerate the training in spiking networks, how do you come up with more SNN friendly temporal architectures that can further give you energy efficiency benefits. Then of course thinking about novel applications for spiking networks beyond standard image recognition scenarios, thinking about, let's say, using time series data, using the data from dynamic vision sensors instead of your standard RGB camera sensors. And finally, also thinking about using these models for more realistic edge constraint settings like distributed learning, wherein your edge can have extreme resource constraints, like your edge might have a memory of just 1 MB and power constraints of just 1 watt. So how can you still do training and inference alongside these extreme resource constraints? And finally, when we are thinking of deploying spiking in these distributed learning scenarios, we are not only thinking about efficiency and accuracy, but we are also thinking about the robustness related aspects, as in privacy of these models. Are we leaking the data when we are communicating between the local clients and the cloud? So how can spiking networks and temporal dynamics in the spiking networks help us reduce this kind of data leakage and give us more privacy, is also something we are investigating. And then, as I said, we are also looking into the hardware related things. So while we are developing all these interesting algorithms, there is a need to start thinking actually bring out energy efficiency when implemented on hardware. So to that effect, we are developing the right type of benchmarking platforms, both on standard CMOS arrays, both standard CMOS based as well as more in-memory computing based. And then while we are developing hardware for some of these algorithms, we are also thinking about co-design approaches, looking into sort of like, co-optimization strategies wherein you optimize both the hardware and the algorithm together, such that you can get an optimal trade-off between energy, delay, area, as well as accuracy. And finally, as I said, like robustness was one of our goals in our algorithm thrust. So trying to think of how do you imbibe robustness when you actually put these algorithms on hardware, and in such a way that the variabilities that are very much predominant in any kind of a hardware, how can you take that variability and try to see if you can address some of the software related vulnerabilities, which can be from adversarial attacks, attacks from using some kind of weight perturbations or input perturbations. So the idea is, when you put these things on hardware, using the variability inside the hardware, can we actually come up with some hardware driven schemes to improve the robustness of these models? So of course, while I give you an overview of some of the research directions in our group, in the interest of time today, I'll be focusing on some algorithm directions that have allowed us to really scale up spiking neural networks for diverse learning scenarios. Similarly, I'll be talking about some of the interesting insights we found by doing hardware-related benchmarking of these spiking neural networks. And finally, I'll be shedding light and talking about some of the interesting challenges that arise today and what type of future work we can do in this direction. So before I go further, I first want to highlight some of the fundamental differences between a spiking network and an artificial neural network, so that we all come under the same page in terms of how spiking network are actually different. So spiking network, if you see, in terms of architecture, they're the same. But what is different is that here they are processing information over a period of time. And this information is just binary information. So wherever you see this red line, that's essentially a binary event 1. And when you don't see that line, it's 0, right? So this binary spike information comes over a period of time. And that, because of the fact that now you're doing temporal processing, you have to have some kind of activation function or neuronal activation that can take account of these temporal correlation between the spikes in the spiking information that is coming in. So the most popular neuronal model that is used today is the leaky integrate fire model, as shown here. And the leaky integrate fire model is nothing but essentially you have this quantity called membrane potential, and this membrane potential integrates or leaks in the presence or absence of spikes. And whenever this membrane potential crosses a threshold, that is an indication that the output spike will be generated, and this output spike is then communicated to the rest of the network. So this is a basic functionality of an SNN. Otherwise, you have the same weighted summation, everything else is the same. It's just that the neuronal functionality and the way in which inputs are processed and outputs are processed differ. Now, one thing I want to make note of here is that because of the fact that we have to use a thresholding operation in order to generate an output spike from the neuron, so the thresholding function is not compatible with standard backpropagation or a gradient descent based training. So to that effect, there is a lot of research that is happening in over the last few years in order to accelerate training of spiking neural networks. Now, while I will shed light today, I'll talk about some of these spiking neural network training techniques. Before that, I would just want to talk about how exactly can you take information that is present and encode them as spiking, binary spike trains. So some of the popular schemes today that are used is rate coding, wherein basically you take any image as shown here, and every pixel of that image will be converted into a spike train, wherein the frequency of spikes in that spike train is proportional to the pixel intensity. And if you think about it, if you do this spike train collection over a large amount of time steps, then you see that over a period of time, the rate coded spike image more or less looks similar to the original image. So the temporal integrity when you do this coding is still maintained. Similarly, there are other coding schemes like direct coding, wherein it's similar to rate coding. The only thing is that you don't convert it directly into spikes, but rather have a learnable encoding layer before an LIF layer that will generate the spike train. And finally, there is temporal coding, wherein the timing of the spike itself carries information. But today, most of the state of the art works today focus on rate coding and direct coding because they have been shown to give you state of the art results. So coming back to my main point that, there is a good amount of research happening in terms of training spiking neural networks. So over the years, people have come up with various different schemes. So first, people try to look into a more bioplausible learning scheme called spike timing dependent plasticity. But turns out that with spike timing dependent plasticity, while you can do unsupervised learning, it is very good for online training on hardware. But the accuracy with these models can be limited because you cannot scale them up. So then people looked into conversion schemes wherein you take a trained artificial neural network and convert it into a spiking neural network. So it turns out that you can really get state of the art accuracy on large scale model implementations using conversion. But in order to retain the accuracy from the ANN into the SNN during the conversion, you really have to process the input for really large number of time steps. And longer time steps means longer latency, and that will again translate to energy consumption. So today, there's a good amount of work that is happening in coming up with backpropagation techniques for spiking neural networks, because that gives us an advantage of actually leveraging the timing information of the inputs in order to come up with some interesting model. And that also allows us to lower the number of time steps required. So training from scratch using backprop through time that leverages time statistics can not only give you efficiency and accuracy trade-off benefits, but can also have some interesting benefits, for example, like adversarial robustness that I will point out later today. So on that note, given that, backpropagation through time-based learning was one of our key direction of research. So one of the first things that we did in our group was coming up with a more scalable training mechanism for spiking neural network that can help us explore more diverse learning strategies and applications. So that the first learning technique we developed was called this batch normalization through time technique. And the idea was that with BNTT, we were able to incorporate good temporal statistics during training. So if you know this, batch norm was a game changer in the ANN world, which basically, by using batch norm, you can really accelerate the training and help the ANN model to get to a good convergence very quickly. But turns out that at this point of time, when we were looking at this work, which was in the year 2020, 2021, batch norm was not very well explored in the spiking domain. And what we came up with was this BNTT model, which is similar to what you would do in a traditional ANN batch norm. But the only difference is that now that in the SNN inputs are coming over a period of time, so it makes sense that the learnable parameters of this batch norm layer inside the SNN, which is this gamma learnable parameter, that should also vary or evolve over time. So by having these learnable internal parameters that vary over time, the intuition was we can capture the temporal propagation of spikes, and hopefully that can lead to even accelerated training with extremely low latency. So if you see here, in terms of implementation, we basically attach the BNTT layer on top of this weighted summation operation coming from the previous layer. And this gamma parameter is also getting learned while we are learning the weights of the neural network. So what we found out after training this spiking neural network with BNTT was that, first of all, we were able to reduce the training latency from previous techniques, like previously conversion techniques and standard surrogate or approximate backpropagation techniques were using on the order of 1,000 or 100 time steps. But with BNTT, we were able to reduce the latency almost to like 25 time steps and still get very good accuracy results, as you can see. Now, the other thing that we also saw was that, with BNTT, we saw this very interesting temporal propagation of spikes. So what I'm showing you here in this graph is the spike activity of a trained model over a period of time. So you see that for both conversion and standard backpropagation, you see that the spike activity is very low in the initial time steps, and then it reaches some kind of a saturating activity after a few time steps. Whereas with BNTT, you have this kind of a rise and fall, this Gaussian-like trend, wherein, like, the early layers spike first and the later layers then spike later. So to understand this further, we actually plotted what I'm showing you here. We plotted in this color chart what is actually the value of gamma that is learned after training using this BNTT learning rule. So what I'm showing you is the values of gamma learned across different time steps for different layers in this spiking neural network. And what we find is this: there is this time shift of the maximum gamma. That means conv layer 1 has maximum gamma at time step 1, conv layer 2 at time step 5, conv layer 3 at time step 8, and so on and so forth. So what is this telling us? And we know that the gamma parameters is attached with the incoming input, weighted summation input. So that means higher the value of gamma, more will be the chance of firing of a particular neuron. So this means that, the early layers are spiking first and the later layers are spiking later. So there is this temporal propagation of spike information as we go deeper. Now, this also makes intuitive sense in our mind, right? Like, early layers should spike first and then the later layers should spike. But the fact is that only with BNTT, we were able to capture this intuitive temporal propagation, which was earlier not being captured. And turns out that that actually is the reason why we were able to get state-of-the-art performance with very low latency. And as you can see here from the experimental results, BNTT trained models, we were able to get very good results on large-scale data sets like TinyImageNet, and in fact get state-of-the-art performance than previous techniques. Now, accuracy-wise, we are good. What about energy efficiency? So we have already reduced the latency, but turns out that in addition to latency, with BNTT models, we were also able to reduce the overall spike rate. And spike rate reduction means that there will be a more sparsity in terms of activity in the network, and sparser the network, more will be the energy efficiency. So we found out that BNTT reduces the spike rate of of these models compared to previous methods by almost 50x and 10x. And then another interesting side effect of this BNTT model we found was robustness benefit. So what we saw was that when we were adversarially attacking the inputs of BNTT trained models and comparing the same with respect to an ANN which is getting attacked in a similar way, we found that, under adversarial attack, a standard ANN will start seeing a drop or a decline in accuracy. Whereas with BNTT models, we found that the accuracy with mid-level attack strengths is pretty much resilient. Whereas if we go beyond this mid-level attack strength to very strong attacks, we found that the accuracy drop is less than 5%. So this again is an interesting advantage, that as soon as you start incorporating temporal statistics during your training, you can get not only efficiency and accuracy benefits, but also some interesting robustness benefits. So given this workhorse of a training algorithm that we found using BNTT, then we started thinking about, okay, now let's expand to new applications. So we now looked into like, more complex classification tasks like image segmentation and video data. Image segmentation is actually very difficult because you have to do pixel wise classification to do this. So we found out, we got state of the art results there. And we also expanded not only from your traditional static image classification to more like classification using some interesting data sets collected using these dynamic vision sensor cameras. Now DVS cameras capture these very sparse events over a period of time, and since they capture temporal events, they are a good match with spiking neural network in general. And we found out that by using the right kind of training algorithm and combining these training algorithm with some interesting data augmentation schemes that work with event-based data sets only, we can actually further reduce the overall latency of the spiking neural network while getting state-of-the-art improvement. That means we got almost 30% improvement over previous state-of-the-art when we looked into these data augmentation and BNTT schemes on event-based data sets. Then another application that I also want to talk about is this human activity recognition. So human activity recognition is what is currently happening on my smartwatch when it is telling me, it's a time to stand up, it's time to run, it's time to sleep, etc. So there is an accelerometer or gyroscopes that are there in our smart devices that are capturing this information over a period of time. And basically there is some kind of a network that we can use to take that temporal data to help us predict, like, whether we should run at this point of time, whether we are walking, whether we are running, whether we are standing, etc. And turns out that as compared to previous works, like, generally, like, with such a kind of time series data for human activity recognition, previous works have mostly focused on ANNs, like, your standard convolutional networks, your LSTM models or transformers. But when we came up with the spike version of a convolutional network or a spike version of a LSTM like model, we found that we not only got state of the art accuracy on these human activity recognition data sets, but the energy efficiency was pretty large also. We got up to, like, 94% reduction in energy consumption as compared to the baseline models. So this again tells us that, SNNs show very good compatibility with data that is low dimensional, but long time series. And the good thing about this particular type of low dimensional long time series data is that there is no need to convert your input information into spikes, because already the information is coming over a period of time. So unlike in an image where you had to convert using some rate coding, here there is no need to convert. So the number of ANN and SNN computations will remain the same. So literally that's why we are seeing this almost like, 94% energy reduction. That's because of the fact that the data set itself is so compatible with a spiking neural network architecture. So given this context, again, as I said, like, we not only looked into more difficult tasks, but we also looked into diverse learning scenarios. So we came up with, when we were thinking about, like, why is SNN being more robust? Why are they more accurate? We first thought about, why let's come up with an interpretability tool that can help us identify the region of interest that a network is focusing on when it is making a given prediction. So with the help of that interpretability tool, we were able to do some qualitative analysis on why are SNNs more robust than standard ANNs. Furthermore, we also looked into applying SNNs on distributed learning scenarios, for example, federated learning, as well as we found out that by using the temporal dimension, we can actually perform some encryption along the temporal dimension that can allow the spiking model to be more private, or to basically have less model leakage or data leakage. So on a federated learning front, I'll just give you a very quick preview of what kind of results we got when we applied spiking neural networks with federated learning. And just to give you a context here of federated learning, the idea is that you have these multiple, let's say, devices like mobile phones, and each of these mobile phones are carrying SNNs, and each client or mobile phone is being trained locally with the data set that is available on that phone using an SNN with BNTT training. And then in an intermediate manner, as and when this network is getting trained, you also communicate the gradients from the model, and that gradients is what is getting aggregated at the server, and then again the server broadcasts the overall aggregated model. So you do this kind of local training, communication of the gradients, and then aggregation and broadcasting in an intermediate, in a timely manner. And turns out that if you do this, then you can actually train your overall model on the entire data set without having to share the data with the cloud model. So this is kind of like, federated learning. It's sort of like is a way to kind of preserve data privacy. But we wanted to see, like, if we bring in SNNs into the picture, what kind of advantages we can do. So it turns out that when we do federated training, it turns out that when we are training with less number of clients or mobile devices, in that case, SNNs are actually lower in terms of performance as compared to ANNs. But as soon as we increase the number of participating clients in the federation to more than 100, SNNs start outperforming ANNs by almost like 30 to 40%. So at scale, SNNs start outperforming ANNs, and remember that these SNNs are being trained using BNTT. And then, of course, given that we are using SNNs at the during inference also, so we will have a good amount of energy efficiency benefits. And when we try to estimate the overall energy efficiency of this federated learning system on a 45 nanometer CMOS process, we found that SNNs were 5 times more efficient than that of a corresponding ANN baseline. So the key takeaway from this BNTT work was that, coming up with the right optimization strategy, we were able to reduce the time steps. And given that this training was leveraging the time statistics very well, we were also able to reduce the spike density that translates to energy efficiency. But the question then we asked was, is spike rate reduction enough for efficiency, or can we further sparsify the SNN in terms of, let's say, weight sparsity or temporal sparsity? So to that effect, one of our recent works, which we actually presented last month at ECCV, diverges into this kind of a pruning of spatial as well as temporal dimension in spiking neural networks. And in this kind of a pruning case, what we were investigating is lottery ticket hypothesis. So lottery ticket hypothesis is a very well-known technique that says that within any dense model resides a very sparse submodel that can be trained to the same level of accuracy as that of the dense model. So the idea was that, will this hypothesis, if we apply the same hypothesis to SNN, will it work? But given that SNNs have a temporal dimension, then why should we just prune along the spatial dimension? That means, why should we just prune the weights? Shouldn't we also prune along the temporal dimension? And that would allow us this 2 degrees of freedom in order to further improve the efficiency when we are doing this pruning technique. So to that effect, what we came up with is this, we proposed this lottery ticket hypothesis method called early time ticket. And here the idea was that when we were trying to, first of all, lottery ticket hypothesis is an iterative pruning strategy. That means you have to first prune the network, then train it, then reinitialize it. And again, you have to go through it. You have to do this in a cyclical manner. But what we found out was that when we are doing this kind of pruning strategy, and when we are trying to find the sparse subnetwork from the dense network, we really do not have to find the sparse subnetwork using the full time horizon, but we can find the sparse subnetwork, or the what are called these winning tickets can be found out from a network which is trained with smaller number of time steps. So using a smaller number of time steps, we could train and find the sparser subnetwork. And finally, once we found the sparser subnetwork, that sparser subnetwork was trained with full number of time steps to convergence and get the right accuracy. But turns out that because of the fact that now we were doing this search and pruning with lesser number of time steps, we were able to reduce the overall search time to find that sparse subnetwork or winning ticket. So as you can see here, as compared to different variants of lottery ticket hypothesis, which is iterative magnitude pruning, IMP, or early bird, we were always like, almost half or 41% reduced. We always had 41% or almost 50% reduced search time. And on top of that, as you can see from the accuracy curve here, our early time tickets always gives us almost 97% sparse models, while almost getting ISO accuracy or less than 1% accuracy drop as compared to the baseline. And then again, this result here is just showing that as compared to prior state-of-the-art works on SNN pruning, given that we were pruning along both the temporal as well as the spatial dimension, we were actually at the same level of sparsity. We were able to get not only sometimes matching, but sometimes better performance than that of the baseline using our temporal and spatial pruning method. So far, I hope that I have been able to convince that SNNs do offer an energy efficient alternative, and from scratch training techniques that use temporal statistics can really make a difference in widening the use of SNNs. But is better training optimization the only way to enable spike-based machine intelligence, or is there something else? So let's try to look at the whole picture. So if you look at the fundamental differences between SNNs and ANNs, so on the structural and functional side, as you can see, there is a difference. So on one side, we have LIF, on the other side, ReLU, on one side, temporal processing, on the other side, static processing. But despite of these differences, all previous SNN works, they all utilize ANN architectures like VGG, ResNets. Even the ones I have talked about earlier, they're all on these ANN architectures. So what we thought of was, because of this difference, there may be an unignorable architectural gap that can lead to a suboptimal solution. So why don't we search for a SNN friendly architecture? So to that effect, we used this neural architecture search technique, a NAS technique, to find these SNN friendly architectures. And the first question before we looked into the NAS for SNNs was, what type of a NAS algorithm will be suitable for SNNs? So inspired from recent work that does this NAS without training, and I'm not going to go into the details of the methodology, but essentially you can calculate this similarity score matrix, and that similarity score matrix will tell you whether any subnetwork that you initialize from a super network has a distinctive activation pattern at initialization, and those distinctive activation pattern at initialization is an indicator whether or not that network will have good performance post training or not. So the method was inspired from this ICML 2021 work, but of course we had to change it slightly to make it more SNN centric. But the idea was that here we were not doing any sort of a training to come up with this searched architecture. We're trying to do like a non-training based or a zero-shot NAS approach, as we call it. And then when we were looking at this search space, we used a cell-based NAS search approach, wherein we were trying to not only find the type of connectivity, but also the type of connection. So in terms of connection, we are looking into whether the network should have 1x1 convolution layers, 3x3 convolution layers, skip connections, no connections. And in terms of connectivity, what we did was we not only search for forward connections, we also search for what we call as backward connections. And what do you mean by a backward connection? It means that information in a later layer at time step t-1 will go ahead and influence the information at an early layer at the present time step t. So it's sort of like the past influencing the present, but the past of the later layer influencing the present of the early layer. So we found out actually that when we did this NAS-based search for SNN-friendly architectures, the type of architectures we got, they gave us state-of-the-art performance across a variety of data sets. And given that now not only we are coming up with a better temporal learning statistics, but also the fact that the architecture also has some interesting temporal information, that also helped us reduce the overall number of time steps. So now we were able to do this training and inference all within just 5 time steps. And turns out we found out the one interesting thing, that SNNs with backward connections are actually preferred more. They give us better accuracy than SNNs with forward connections. And I like actually this interesting architecture wherein this cell and this cell are not even connected, but this cell is sort of talking to the rest of the cell using the, meaning with the help of the backward and the forward connection here. So the fact that, we are able to come up with these interesting disconnected architectures shows that, there is some potential in leveraging temporal statistics. Finally, some of the things also I want to talk about is that the search architectures were transferable across data sets. That means a network searched using CFAR 10 was transferable to CFAR 100. And finally, given that we were using this NAS without training technique, we were able to find accurate architectures within, within a very less GPU search time. So on a RTX 2080 Ti GPU, the search time was less than 2 hours for getting an accuracy of more than 72 to 74% on CFAR 100 dataset. So all these new architectures that can be that are being founded, they do point to some interesting temporal effects from an algorithmic perspective. But so far, I have just focused on algorithms and I have not talked about hardware. So what about the hardware perspective? Are SNNs truly efficient when implemented on hardware? So we have to check that. So in order to see that, one of the first things we wanted to do in our group was, okay, let's take some existing benchmarking tool that is available and take one of our algorithms and put it on that benchmarking tool and do some energy delay latency area analysis. But turns out that benchmarking tool for SNNs was missing. So the first thing we did in our group was develop two types of benchmarking tools. One systolic array based called SATA, which is based on 65 nanometer CMOS based hardware. And it was a benchmarking platform for SNN training. And the other one was SNN Inference based benchmarking tool, which uses basically a crossbar based architecture platform. And it was called SpikeSim. So very quickly, I'll be giving you the insights and results of these benchmarking tools. So with SATA, as you can see here, it's a standard systolic array-based design. Your processing engine has the functionality to do the multiply accumulate operation, the leak integrate fire operation. Since it's a training engine, we also had to have some gradient update related units so that you can do training inside this engine. But what I want to focus on is the energy and the efficiency results that we got. So we actually compared an SNN implemented on SATA with that of a corresponding ANN of the same type of architecture, everything implemented on Eyeriss like training accelerator. And when we compared an SNN which is being processed for 8 time steps to that of an ANN which has 8-bit precision, we found that without considering any sparsity, that means we are not considering any sort of event-driven sparsity coming from the leak integrate fire neurons in the SNN, we found that SNNs consume almost 1.4x more energy than that of an ANN. And it turns out even when we consider sparsity, that the energy consumption slightly goes down, but it is still more. So SNN now consume 1.27x more energy. So we wanted to understand, like, if there is no benefits in terms of the sparsity, then where is where are the event driven benefits getting annulled? And it turns out that Timestep actually plays a major role in terms of annulling these sparsity related benefits. So remember that in spiking neural networks, we have to do repeated or multiple time step computation. And turns out that whenever you do multiple time step computation, then we have to do repeated memory access from the DRAM to the PE array or the processing engine array. And we have to repeatedly access these membrane potential marked as U's and the spiking information, which is marked as S. And that memory access is going to dominate the energy cost. So no matter what, as and when you increase the number of time steps, you will have a much larger energy gap between the SNN and the ANN. And in fact, the training latency gap as we increase the number of time steps also grows. So low time step is always preferred for not only latency minimization, but also energy minimization. But then the question is, can we actually get some advantages from sparsity? So turns out that there is this quantity when you're training an SNN, this gradient of the membrane potential is actually, it turns out to be a sparse quantity. And it turns out that if the gradient of the membrane potential, this delta U quantity, if it has a sparsity more than 88%, then it turns out that the SNN will start winning over an ANN in terms of computation energy. So again, using this benchmarking tool, we were able to not only see what was the main challenge, but we were also able to see, like, what could be one possible direction such that could help us with a new algorithm design such that we can have actually SNNs that are winning over ANNs when we are thinking about training. So the idea with SATA or SpikeSim later on is to use them as, platforms or baselines to measure the energy efficiency gain, and that can hopefully design or help us design better SNN algorithms for getting more energy efficiency. Similarly, SpikeSim, as I said, again, I'll be only focusing on the main insights from this tool here. But with SpikeSim also, as I said, it's a standard IMC based implementation tool wherein you have this tiled array architecture. Each tile contains an array of P's. Each P contains an array of crossbars as shown. And then, of course, because of the in this tool, we do hardware realistic inference. So during real-time NOC trace generation, real-time energy latency and area calculation can be done. So we have built this tool to do more real-time analysis. And one of the first analysis that we did using this tool was that when we did the area analysis of any spiking neural network, let's say as shown here, a VGG9 or a VGG16 type implemented on a SpikeSim tool, one of the first things that came out was that the LIF or the neuronal module area is pretty large. I mean, neuronal module consumes more than 30% of the overall area distribution. And this is absolutely non-existent in the case of an ANN, because in an ANN, you just, for a ReLU-like operation, you just need a comparator. So this high area overhead in SNN is again coming because of the fact that in SNNs, we have to, in these LIF operations, we have to store the intermediate membrane potentials. And for storing the membrane potentials, we have to have a large SRAM memory. So that again gives you this area related constraint. And turns out that we can do some interesting simple topological modification wherein, let's say, if you reduce the number of channels in the early layers, we can actually reduce the neuronal area as well as the latency as well as the energy as shown here. So by doing this benchmarking, that again allowed us to do some simple algorithmic modification that helped us get again good energy latency area results. And then finally, we also compared a SpikeSim implemented spiking neural network with a standard ANN that is implemented on another benchmarking tool called Neurosim, which is a state-of-the-art benchmarking tool for, again, IMC implementations of artificial neural networks. And here we are comparing an SNN with 4-bit weights and 1-bit spike activation to that of an ANN with 4-bit weight and 4-bit activations. And we found out that for SNNs to have lower latency and lower energy at ISO accuracy with these 4-bit ANNs, the number of time steps that you have to operate is within 4, right? So you have to really, in order to really have SNNs designs that can win over ANNs, your low time step count has to be very, very important. I'm going to actually skip over this slide given that I don't have time. So essentially, I want to kind of, talk about the fact that, so far I talked about the algorithmic perspective, I talked about the hardware perspective, and hopefully this kind of motivates this algorithm hardware co-design directions, right? So in fact, if you look at Loihi, True North, they were a more hardware focused direction, trying to look into small scale optimization tasks, showing that SNNs can have really good energy delay area reduction results as compared to ANNs. And if you think about what we did with SpikeSim and SATA, is looking at more traditional learning schemes like image recognition tasks, etc., and still showing that there is a good amount of accuracy and energy reduction that you can obtain. But some of our key insights still remained is that, when we think about SNNs for edge constraint scenarios, I think it's better to explore simple tasks like human activity recognition, which has this low dimensionality inputs. And finally, one thing that became very clear from our benchmarking was that in order to scale up spiking neural networks for more mainstream tasks, we really have to focus on this memory overhead that is coming up in SNNs, not only because of this membrane potential, but also because of the repeated time step calculation. So to that effect, the future opportunities that lie in this area, and that is something that we are at least focusing on, is to reduce the memory and the area overhead that is coming because of this time step based computation and because of these LIF neurons. And to that effect, like I just want to show like where is this kind of memory overhead coming from. So from a computational graph perspective, if you compare an ANN versus an SNN, so in an SNN, because of the fact that you have to process the input for multiple time steps, so every time the computational graph of the SNN will be T times memory expensive than that of an ANN. Even if the number of layers, everything remains the same, but the time step again will explode the memory. Right. So how can we reduce the LIF memory is the question. So there are a couple of future opportunities that we are exploring. One is looking into this interesting shared membrane potential. The other one is doing dynamic temporal inference. And finally, we can think of some architectural schemes like pipelining the time steps and the layers. So with shared membrane potential, I just want to give you like a preview of this technique. Is that like, the idea is that we, instead of using like calculating the membrane potential for every layer at every time step, what we do is we share the membrane potential of the first layer with every other layer. Right. So basically you're sharing the LIF neurons across multiple layers and multiple channels. And it turns out that with the right kind of objective, like objective function and loss function, we can actually do this. And we can come up with different variants of this sharing mechanism. We can share between channels. We can come up with like a cross layer, cross channel sharing. And the idea with this particular sharing is that we don't anymore have to store all the membrane potential. So in a baseline model, again showing from a computational graph perspective, you would have to store all the membrane potential during forward propagation and during backward propagation. But turns out if you do this cross layer sharing, as I talked about, we just have to store the membrane potential of only the last layer at the last time step. Because once you store this, all the previous layers membrane potential can be back calculated, and we have come up with some theoretical proofs as to show how this reverse computation of the previous layers membrane potential can happen when you're doing this shared cross layer sharing. So again, just showing you some of the major results, we found that like when you're doing this shared sharing of membrane potential in SNNs, we found that the accuracy is actually preserved. It's the same as that of baseline as across different data sets and different architectures. But what is more interesting here, I want to talk about, is that how much memory overhead are you able to reduce? So during your forward step, the memory overhead that you're able to reduce is almost like 4x. But during backward step, because now none of the caching of membrane potential is required, so we are able to reduce the memory overhead by almost 20x. So there is a huge amount of benefit by just doing this sharing. Now, the final thing also I want to just talk about is this very simple input dependent dynamic time step that you can do inference in spiking neural networks. So here the idea is that not all inputs require, let's say, all 5 time steps. Maybe input 1 will require only the first time step. Input 2 might require just 2 time steps. So this is similar to the idea of early exit in ANN literature, but here we are doing early temporal exit. So instead of having all inputs processed for the same number of time steps, we are having inputs being processed in a dynamic manner for different number of time steps. And what we find is that actually in real world data sets, most of the inputs, like almost 90% of the inputs can be inferred at as early as the first time step itself, and only a few inputs require the entire 5 or 6 time steps, the total horizon to do the correct inference. So we are, so again I'm showing you the results here, in the accuracy versus EDP plot, we find that we get very good accuracy with this kind of a dynamic time step inference while getting almost 81% reduction in EDP. So that brings to my conclusion of this talk here. So hopefully I've been able to convince that there is a good amount of potential for edge computing with spiking neural networks, but temporal domain is key, and it remains to be seen whether we are using temporal statistics in the best way, because the type of coding, the type of training, the type of architecture, all of that plays a role. And the question then is, can current hardware be amenable with time step based computations? As we have seen, with new types of benchmarking results, we are actually seeing that there are some interesting overheads that we need to think about when we are doing SNN implementation on hardware. So to that effect, algorithm hardware co-design is going to be very, very essential in the next generation of neural computing. So, so that concludes my talk. Thank you all for your attention. And just want to say that all the work that I presented, the code for most of the work is present, is available in this GitHub link.